This introduction really sets the stage by highlighting a crucial point. Designing data converters, like the ADCs we're focusing on, has become incredibly challenging in the modern era of nanoelectronics. As we shrink transistors down to nanometer scales, we run into some fundamental physical limitations that make the life of an analog designer much harder. Let's look at the specific challenges listed here. The first is low intrinsic device gain. Intrinsic gain is a measure of the maximum possible amplification you can get from a single transistor. As transistors get smaller, this intrinsic gain drops significantly. Why does this matter? Well, data converters are built using amplifiers. If your basic building block, the transistor, is less effective at amplifying, you need to use more complex and clever circuit techniques to achieve the desired performance, which can introduce other problems. Next, we have high nonlinearity. In a perfect world, an amplifier's output would be a perfectly scaled version of its input. That's a linear relationship. But with modern devices, this relationship becomes more curved and distorted, or nonlinear. This nonlinearity introduces errors and distortion into the signal you're trying to convert, reducing the overall accuracy of the data converter. Then there's reduced headroom. This is a direct consequence of lowering the power supply voltage to save power in modern chips. Headroom is essentially the voltage range your signal has to operate within. If the supply voltage drops from, say, 3 volts to 1 volt, your signal has much less room to swing. This directly impacts the dynamic range, which is the ratio between the largest and smallest signals the converter can accurately handle. It's like trying to paint a masterpiece on a much smaller canvas. The fourth challenge is large variability and mismatches. When you manufacture billions of transistors on a single chip, they don't all come out perfectly identical. There are tiny, random variations from one device to the next. In analog circuits, where performance often depends on 2 components being perfectly matched, these mismatches can cause significant errors. Finally, there's the problem of survival in a digital-driven system-on-chip (SoC) environment. A modern SoC is a very noisy place. You have a massive digital processor switching billions of times per second, sitting right next to your delicate analog data converter. All that digital switching creates a huge amount of electrical noise that can easily leak over and corrupt the sensitive analog signal. Your analog circuit has to be robust enough to perform accurately in this hostile environment. So, with all these problems, how are designers coping? This leads us to the trends in data converter design. The main trend is something called digitally assisted analog design. The philosophy here is simple but powerful. Since building a near-perfect analog circuit is becoming almost impossible, let's not try. Instead, let's build an analog circuit that's good enough, and then use a smart digital circuit to measure and correct the remaining errors. And this is all fueled by aggressive device scaling. It's an interesting paradox, isn't it? The very thing that's causing all these analog design headaches, making transistors smaller, is also providing the solution. Shrinking transistors makes digital circuits incredibly fast, dense, and power efficient. So we have an abundance of cheap digital processing power at our disposal, which we can use to help out the struggling analog circuits. This concept of using digital calibration to fix analog imperfections is the core idea we'll be exploring throughout this tutorial.